Hello. This is going to be a quick walkthrough of my code for Lab 7. Lab 7, as I detailed in the hardware demo, is all about using the ADC to determine joystick movement and also print out temperature values. I think this walkthrough is going to be a little shorter than the ones that I typically do because the amount of code that we needed to write for this lab was not as extensive. Anyway, let's get started. So Uh, we'll start with the ADC driver file. The first function that I started with was the ADC init function. It initializes the ADC and then calibrates it. The inputs for the single input for this is the ADC handler. And I configured this pretty much standard to what the instructor provided us, with the one exception of enabling the temperature sensor in the control register 2. Um, and once all of that stuff's done, I just go ahead and use the HAL ADC init function, pass in the handler, and then call the calibrator. From here, I did overwrite the ADC MSP init function that HAL provides us a week for. All this is doing is enabling the clocks for the ADC and then also GPIO A. It enables the clock for port A. And then obviously we have pins 0 and 1 configured as inputs with analog mode. And those are those are the pins that are defined in the documentation for our board for ADC1 channel 0 and channel 1 respectively. So I have that right here. I go ahead and init those GPIO and then return. I have this ADC read pulled function that Gary provided us. Uh, this basically reads and returns a value into, it chunks that value into the address for this ADC val that we're sending in. Looks like he's using just basic HAL functionality for doing this. One of the new functions I wrote was the get average value function. And what this does is we pass in a channel and the ADC handle, and it reads 16 samples of that channel, and then accumulates that into a running average, and then returns that running average divided by 16. The point of this was to kind of get rid of like noise in in every poll that we do. So I noticed when I started up my ADC that even in idle mode, the value was just jumping around all over the place. So I figured a good way to get rid of that would be to take an average value. And I settled on 16 because that's kind of a that's a value that I've used at work for a lot of the analog front end systems that I work with on FPGAs. We typically take 16 samples and then bit shift them and then return. So I figured that was a pretty good place to start, and it's working fine as far as I know. So I've decided to do it that way. Um, so instead of actually using the read pulled function for all of my reads, I just read average values. This allows me to kind of um, iron out a lot of function calls between when the user is still moving the ADC, for instance. So if we're going from idle to like a position where the ADC is kind of only the joystick's only kind of tilted in one direction, this lets me iron out a lot of the function calls that would be made with the if else statements that I have in my control. Um, so this is just for normalization, I guess. And again, I do 16 reads using the instructor provided ADC read pulled and accumulate that into a running average, and then I bit shift that um, to the right 4 times and then return that value. And then finally, the only other value I really have is the ADC raw to float. And what this does is it normalizes it to the 3.3 volt range. The way I do that is I take the maximum value of 2 to the 12th because we have a 12-bit ADC, and then I divide the raw value by 4095, and then I multiply it by 3.3 and then return it. Pretty standard. Um, that looks to be about all I did there. Um, and then obviously I have a accompanying header file for all the stuff that I'm doing here. I'll get into main over here. Um, this one's getting to be a little on the large side. So basically all I do here is set up my variables over here for all of the stuff that I'm doing. We have the x-axis ADC channel values. I have a raw value. I have an idle value. I'll talk about that in a second. I'll talk about x previous in a second as well. I have ADC value float, and then I have a value for determining when I last did an update. I'll talk about how I'm using all of these variables in a second. And then I have y-axis counterparts for this, raw y-ADC value, y-idle value, um, previous y value, and then floating y-ADC value. For the temperature sensor, I have a raw value, a floating point value, and a Celsius value. And then I have a unit that I'm calling last temp. So basically I start off by taking 16 samples in idle. And the idea behind this is I get an average value for what the joystick is idling at for both the x-axis and the y-axis. Since it's jumping all over the place, this gives me a better sample to kind of compare my readings to. And I do this before I even get into my while loop. And I just save these off. And the idea here is that by saving them off, by saving them off, I can kind of use this with different joysticks. So not all of the joysticks have the same type of potentiometers within them, so they might return a different value. But if I replace the joystick that I'm currently using, I should be able to still go ahead and do all the functionality here. So I start off in my while loop, which is basically the main control loop, by reading the raw values for both the x-axis and the y-axis. And you'll see here that the x-axis is mapped to channel 1, y-axis is mapped to channel 0. And from here, I kind of look to see if we're in the auto count mode. And if we are, we really only care about the x values. So I started a comparison between the x value that I read and the idle value. So if the x-axis value is greater than the average x idle value, then I start a comparison for determining the speed. If the x-axis is tilted all the way to the right, if the joystick's tilted all the way to the right, that gives us a value close to the 4095 range. It's saturating the 16 bits. So what I do here is I subtract that value from the value that I read from the idle value, and then if it's all the way to the right, I set the counter speed to 250 milliseconds. And what I'm doing here is I'm kind of bypassing using a separate counter for updating the counter value. Since we're not actually incrementing, I need to do a fake increment kind of. Um, and I do that by using the get tick function. I get the tick and then I check to see when the last update happened. And if the difference between these two values is greater than the counter speed, then I go ahead and update the counter by incrementing it. And then I also update my actual periodic timer. The reason I do it this way is because the periodic timer is what's handling my GPIO rights for updating the LEDs. So I'm doing that inside of my IRQ handler. I figured this was the most intuitive place to do it. So instead of ka-chunking all of this code into this file, sorry, where'd it go? Sorry, into this file, I figured why not just update the periodic timer? But this got a little tricky because the periodic timer only needs to be updated once for every tilt. Otherwise, you start seeing some undeterministic behavior on the LED outputs. So that's why I had to had to resort to using this HAL get tick. I guess another way of doing this would be to I'm honestly not sure what other way to do this would be aside from using a separate counter. I just didn't want to get into that, so I just go ahead and use HalGetTick and then compare it to when I last updated, and if that's comparable to my counter speed, then I go ahead and increment my counter value. And I'm doing that for different differences between the raw value and the idle value. So obviously, if we're tilted all the way to the right, we're incrementing at 250 milliseconds. But if we're a little further to the left, then we increment at 500 milliseconds. And then I set the lower bound here to be 1.25 seconds. And then I have similar logic for tilting to the left. The only difference really is that it subtracts as opposed to adding. And of course, I subtract again x idle from x ADC val raw, and then depending on that, it goes ahead and decrements. And then if we are in increment mode, the only thing we really care about is the y-axis value. So for the y-axis value, what I do is I check to see if the user is tilting it in either direction. So if the user is if the user is tilting it in such a way where we're getting a 1 volt difference between idle and the value that they've twisted it to, that they've tilted it to, then I go ahead and sit in a loop and wait for them to return to idle. The way I'm doing this is I take the y idle value that I used for calibration earlier on, and I keep reading values from the ADC, and then if they're within 50 of each other, then I know that we've returned to idle. The way this the reason this lets me work the reason this works is because we're getting average values. They should be within a few counts of each other. And 50 is I noticed a range that the user wouldn't really be able to tell. Like even if you tilt it just a little, you're probably going to go up by like 200 or 300. You wouldn't the joystick's not so sensitive, so this ends up working out all right. And then obviously have bounds for the counter speed. And if the counter speed's at 250, then we can't decrement the counter speed. And the lower the counter speed goes, the faster the LEDs update. So I guess really what I should have called this is like counter rate or something, or like seconds rate or something. I don't know. But this is basically a millisecond representation for how fast the LEDs update, and it's bound at 250 milliseconds at the lower range. Then we go ahead and update the periodic timer, and then I'm doing the same thing for if tilted down. So if the user tilts it down, then we set an upper bound of 2000 milliseconds, and we're incrementing by 250 milliseconds every time they tilt up. And again, I wait for the user to go ahead and get back down to the idle position before updating the periodic timer and the counter here. So the last thing I do is I print out the x-axis and y-axis values every time the difference between the raw value and the previous value is greater than 250. So basically how this works is I don't actually do a floating point conversion unless absolutely necessary. I wasn't really interested in working with the floating point conversions. Um, Thinking about the ADC values as digital values made a little bit more sense in my head, so I just went ahead and did the logic that way. But basically, I take the absolute value of the difference here. I set this value to 0 at the beginning, so this always triggers when the user first starts up the program. But what it does is if the difference between the raw values is 250 or more, sorry, if it's greater than 250, then we go ahead and do this print. And 250 volts amounts to about, if I recall correctly, zero point 0.1 volts or so. So that's pretty good, I think. Whenever the voltage that the ADC is reading changes by zero point 0.1 volts, it'll print a value out. And I'll go ahead and demonstrate that actually. Let me start up. I'll let that do its thing in the background. Um, and I'll bring up my terminal to show that that's working. Sorry, serial port needs to be at this. Um, might actually be running. Yeah, so it's printing out the temperature actually. So it's already running in the background. So you'll see here that as we update and the values change by point point one, they do end up printing out. Um, sorry, point two. Point two is the value that I was talking about, not point one. I messed that up. But obviously, if I tilt down, then you can see the y-axis changing. Then if I let it go, it goes back to the idle position. And then if I tilt up and then back down, then it prints out, and then left and then right as well. So it prints out those values. And then obviously the last thing to do was to print out the temperature of the board. For this one, what I do is I print out the temperature value of the board every 5 seconds. So I'm utilizing getTick again. And what I'm doing here is I'm comparing it to that last temp value that I variable that I used. Once this criteria is fulfilled, I go ahead and read the ADC temp sensor, and I'm not doing an average value here. I convert it to a floating point number, and then I convert it to Celsius using the function that is provided by the documentation. I pulled out these nominal values from the 103R documentation. And then finally, I convert that value to Fahrenheit by multiplying by 1.28 and adding 32. And then I update the last temp value and just let this sit in a loop. And that basically does it basically prints out the temperature in Fahrenheit here. And then obviously we demonstrated that that moving around the joystick does print out updated values, both the raw value and the voltage value here. I think that about covers everything I needed to cover for this code walkthrough. Hopefully I answered anything that might have been left up for question, but if I missed anything, don't hesitate to reach out. But yeah, thanks.